And our next speaker is Pasnoori from Rutgers. He's going to talk about topological phases in strongly correlated 1D systems.
Thank you, Professor Coleman.
And
so today I'm going to be
minutes.
talking about topological phases in strongly correlated one-dimensional systems. I'm going to focus on the 1D superconductor coupled to magnetic impurities at both the edges. The strong correlations in the bulk and at the edges gives rise to a symmetry-protected topological phase in which there is an emergence of boundary supersymmetry and the edges are entangled. This supersymmetric algebra can be reduced down to the Clifford algebra, which corresponds to the appearance of Majorana modes when the symmetries at the edges are broken. This can be achieved by applying strong magnetic fields to the impurities. And this system has applications in topological quantum computers. So before talking about the system, let me talk about how a magnetic impurity interacts with a bath of non-interacting electrons. A quantum impurity interacts with an electron through spin exchange interaction, in which the coupling constant J is taken to be positive, which corresponds to the antiferromagnetic nature. A well-known effect called the Condo Effect takes place, in which the strong coupling Condo scale called the Condo temperature arises. In this many-body effect, the impurity correlates many electrons and thus forms a Condo cloud, which then screens the impurity. Now, what happens to this phenomena when one introduces interactions between the electrons? To study this effect, we couple a quantum magnetic impurity to the edge of a one-dimensional superconductor in which there are strong electron-electron correlations and which leads to high quantum fluctuations. Now, the one-dimensional superconductor in which the charge is conserved is described by these two terms. The H naught describes the right and left moving fermions with spin, and the H int describes the antiferromagnetic interaction between the electrons. And this models the superconductor in the spin singlet phase. The spin and charge degrees of freedom are decoupled, and the excitations in the charge sector are gapless and are called holons, and the excitations in the spin sector acquire a gap and they are called spinons. This gap is dynamically generated by the interactions in the system. And the order parameter is quasi-long range. Now, to this system, we couple a magnetic impurity at the edge, which interacts with the electrons through spin exchange interaction. Now, unlike the metallic case, this system exhibits three regimes depending on the relative values of the bulk and impurity coupling strengths. And this model is integrable for arbitrary values of G and J. There exists an RG invariant parameter, which is a function of both impurity and bulk coupling constants, and it can take real and imaginary values. And this can be used to label these three regimes. When the impurity is strongly coupled to the bulk, the Condo regime occurs, and the YSR, which stands for Yu-Shiba-Rusino regime, occurs when the impurity and bulk are moderately coupled. And when the impurity is very weakly coupled, we have the unscreened regime. In the Condo regime, due to the strong coupling of the impurity with the electrons in the bulk, the Condo effect takes place. But now we have the interactions in the bulk, so the Condo temperature is renormalized. Looking at the ratio of the density of states of the impurity in the bulk, we see that there is a resonance peak indicative of the Condo effect. Now, the Condo temperature can be calculated by looking at the width at half maximum of this peak, and we obtain such a form for TK. In the limit, when the impurity is very strongly interacting with the bulk electrons, the gap in the bulk should not play a bigger role in this boundary effect, and the TK takes asymptotically form of the TK of that of a metal. And now, as we decrease the impurity coupling strength, we reach the other end of the Condo regime where delta becomes equals to TK, and this occurs for the value of A equals to half. In this limit, the Condo cloud, which is the result of a many-body effect, smoothly turns into a spin accumulation corresponding to a one-particle bound state. And as we decrease the impurity coupling strength further, we enter the YSR regime. In this regime, there is no Condo effect and there is no generation of the Condo temperature, but the impurity is still screened by this local spin accumulation, which can now be removed, and hence one can unscreen the impurity, and this costs energy less than the superconducting gap, and hence these states whose energy is less than the gap are called YSR intragap states. There exists a first order phase transition between the screened and the unscreened states at A equals to 1, where the ground state is threefold degenerate, and as we decrease the impurity coupling strength further, we enter the unscreened regime. In this regime, the correlation between the impurity and the bulk is not strong enough to completely screen the impurity, and there are no bound states, and the ground state is doubly degenerate, with total spin being plus or minus half. Now, much work has been done in analyzing the Condo effect in the BCS superconductor, where in contrast to our case, the YSR states exist everywhere for all values of the coupling strengths. But as we've seen in our system, the YSR states exist only in the YSR regime, which is a very narrow region situated around the phase transition line. Hence, in our system where the quantum fluctuations are really strong, the YSR states are destroyed in most of the phase diagram. Now, what happens when you couple another impurity to the other edge? It turns out that the model is integrable for arbitrary values of JL and JR, the two impurity coupling strengths, and there exists two RG invariant parameters, AL and AR. And the phase diagram of this two impurity system is rich, and it has many regimes depending on what regime each impurity is in. The most interesting regime occurs when both the impurities are in their respective YSR regimes, which is shown in green color. In this regime, a symmetry protected topological phase occurs, and there is an emergent boundary supersymmetry, and the edges are entangled. And this entanglement of the edges and the occurrence of this SPT phase is not possible when only one impurity is coupled. So we need both the impurities at two edges in order for us to have such a phase. Now, there exists 9 states in this regime, and each state is mapped to another state through these Hubbard operators, which satisfy the supersymmetric algebra. And to see the entanglement of the edges, one can construct the irreducible representations of this algebra. But here I'm going to take a special limit of the system wherein the entanglement can be seen easily. One needs to use Holstein-Primakov representation in which each edge has one fermionic and one bosonic operator. The fermionic operator corresponds to adding a bound state with a particular spin, hence it screens or unscreens the impurity, and the bosonic operator flips the spin of the unscreened impurity. Now let's freeze these bosonic operators by, let's say, applying strong magnetic fields to the impurities which lock the spin. Now, this breaks the SU2 symmetries at both the edges, and the effective boundary Hamiltonian can be written down like this. And these bound state operators commute with the Hamiltonian, which gives rise to an effect in which the Hilbert space breaks down into 4 towers. And each tower is labeled by a local fermionic parity quantum number. And the total fermionic parity is a conserved quantity, and it's a product of the local fermionic parities. Now, one can fix the total fermionic parity and change the local fermionic parity on one edge. And this automatically changes the local fermionic parity on the other edge. Hence, we can see that the two edges are entangled. Now, these operations are performed by these Marana operators, which satisfy the Clifford algebra. And these operators take a state in one tower and map it to a corresponding state in the other tower. So in conclusion, we see that by introducing these quantum fluctuations at both the edges of a seemingly simple superconductor in spin singlet phase, we see that there is an emergence of boundary supersymmetry, and the entanglement of the edges occurs. And in a special limit, the system gives rise to the well-known Marana modes. Now one can question what happens when you couple multiple impurities or many impurities to the superconductor. One would expect that there would be a hybridization of these YSR states, and there would be an effective interaction between the impurities depending on the separation of them. And the topological properties of such a system would be very rich. And this would be the future direction of our research. Thank you for having me.
Okay, thank you very much. Questions? Well, let me ask a question. There really aren't any true 1D superconductors as far as I'm aware. So have you put any thought into what might happen if you made this quasi 2D, if you had, I don't know, your wire connected to a bulk that was superconducting?
Yeah, so if you kind of proximity couple a wire to a bulk superconductor of, let's say 2 or 3 dimensions, the quantum fluctuations wouldn't be as strong because you can model that system through the proximity coupling, and you can use mean field approaches, right? And in such a system, these quantum fluctuations wouldn't be strong, and I doubt that this phase structure that we have here would appear in such a system.
I see. And the Majorana fermions you have at the end?
So in our system, what I've taken is a special limit. So let's say you take a 1D wire and then just apply some strong magnetic fields to the edges. Then you would see the emergence of Majoranas. You don't really need any quantum impurities.
I see. Okay, thank you. Any other questions? Okay, well, thank you very much, Parameshwar.
Thank you.